Sauce here. This is a video lesson on law of sines. I'm going to begin by making a diagram of a triangle so we can use it to discover some equations that are very powerful and useful. I'm going to label the vertices of this triangle A, B, and C. And by convention, the side that is opposite is labeled with the same letter, but in lowercase. So this will be side C, since it's opposite angle C. And side B, opposite angle B. Side A, opposite angle A. We're going to include a dotted line that is perpendicular to side B and label that H as the height of this triangle. Familiar formula for the area of a triangle is area is equal to 1/2 times base times height, where the base and the height are simply perpendicular to each other, and the base is a side of the triangle, where B is the variable in that equation, is a side of the triangle. This formula for the area of a triangle is very useful, but it's dependent on one of the measures which is not either a side or an angle of the triangle. The height of the triangle is often inside the triangle and is not a part of the geometric structure of the triangle itself. If we think of the triangle being the measure of the three sides and the measure of the three angles, we can do better than this formula. I'm going to observe that in this diagram, two right triangles were created inside. And with right triangles, we can use trigonometry. I can observe that if I take the sine of angle C, it's equal to the ratio opposite over the hypotenuse of this right triangle inside, or sine C is equal to H over side A. I can modify what I have here very simply by multiplying both sides by side A to get A times sine of angle C is equal to H. And in the formula, the familiar formula, area is equal to 1/2 base times height, I can substitute what H is equal to in for H to produce a new formula for the area. Area is equal to 1/2 times side B, and then substitute side A, sine angle C, for H. This formula some would consider to be better because the variables in it are the actual sides of a triangle and an angle. As long as you have two sides of any triangle and the angle in between those two sides, you can calculate the area of that triangle and not have to have some height that is not a part of the triangle or the given information. That was an exercise in observing relationships between the sides and angles of a triangle to give us a useful formula. But we're going to do it again in a more sophisticated way to produce something that, though it's a mathematical equation, was so impressive to the people that first discovered it that they called it a law. And it starts this way. Again, with the observation that if I take the sine of angle C as the opposite H over the side A in this right triangle, then I can do it again, or the similar observation with the other right triangle, and write the sine of angle A is equal to the same opposite H over its hypotenuse C in the right triangle here. And both I will solve for H by multiplying the first case by A like I did before and the second case by C. to get side A times the sine of angle C is equal to H, and side C times sine of angle A is also equal to H. And when two things are equal to the same thing, they're equal to each other. I can take this equation, these two expressions both equal to H, and show that they must be equal to each other. And then, because on both sides of this equation we have a combination of A and C, I'm going to divide both sides by A to clear this factor here, and also divide both sides by C to clear the common factor here. When I do, my choices cancel these out, and I'm left with sine of angle C over the side opposite C is equal to the sine of angle A over its opposite side A. Because this was based on the geometry and measures in general of a triangle, it means that this is true for every triangle. I could go through a similar process with the third angle and side opposite pair B that wasn't used in this process, but I could repeat the process with angle and side B to show that the ratio sine B over its opposite side B is equal to the other two ratios. This mathematical relationship helps solve for angles and sides in triangles, any triangles, and is so useful to help us with the mathematics of triangles that when it was first discovered, they called it the law of sines. The word law doesn't mean that it's any more special than any other equation that's been discovered in math. It was just so impressive they used that word. For example, given an angle of 50 degrees, opposite side measure of 120, and a second angle 20 degrees, find a second side. So, as often is the case when we're given mathematical information in the form of language, it's best to draw a diagram and label the diagram as thoroughly as possible with the given information before attempting to go towards an answer or find an answer. So we must be talking about a triangle. It would have helped for the words to tell us that these were sides and angles of a triangle. But we draw a diagram of a triangle and it says give an angle of 50 degrees. So any angle can be labeled as 50, but the language says the opposite side is 120, so it must be the side opposite the angle that they were given of 50 degrees. And a second angle of 20 degrees. We don't know where it is, so we're going to choose one of them to be 20 degrees. It doesn't matter which. We're expected to find a second side. Well, we have one side labeled 120. We have a choice, it seems, of finding any one of these two sides. But the only side that we're capable of finding would be the side that is opposite 20 degrees. So it doesn't need to say, because it's the only side that we're capable of finding, and we'll have to use the law of sines to do that. The law of sines requires that these ratios come from angle side opposite pairs. So when we say sine of b over b, one of those b's is lowercase and one is capital. They're not the same symbol. They're the same letter because they share a relationship of being a pair of angle side that are opposite. But they measure different things. We call them angle side opposite pair. So when we use the law of sines, we're looking for pairs of angles and sides that are opposite. The 50 degrees and the 120 is one of those angle side opposite pairs. So the side that we're going to find has got to be the one that is opposite this 20 degrees. We'll call it x, because it's the one that's going to be used in the law of sines. With this information, I'll set up the law of sines, taking the sine of an angle that we have, the measure of 50 degrees over its opposite side of 120, must be equal to the sine of 20 degrees over its opposite side that we've labeled x. I have an equation using law of sines with one unknown, so I can solve for and evaluate that unknown x. I'm going to do that by multiplying both sides by 120 and multiplying both sides by x. So I will get x times the sine of 50 degrees is equal to 120 times the sine of 20 degrees. Notice that I haven't evaluated sine of 50 degrees because if I'm going to evaluate trig, it usually needs to be approximated, and I'm in the habit of only approximating if I have to in the very last step so that I am as accurate as possible. X will then be equal to 120 times the sine of 20 degrees divided by the sine of 50 degrees. And finally, if I went to a calculator to approximate the sine of 20 and the sine of 50 degrees, and then multiply by 120, I would get an approximation for x of 53.577. That's rounded to the nearest thousandth, a good habit to be in.